Okay, so question 2.11. A piston cylinder device contains 0.9 kilograms of saturated mixture R134A at -10. The piston weighs 10 kilograms with a diameter of 22 centimeters and it is free to move without friction. Heat is supplied until we reach a temperature of 20 degrees Celsius. Determine the pressure, the volume change, and the enthalpy change. Assuming local atmospheric pressure is 97.5. It's a bit lower than we normally assume it to be, but that's okay. So in the case of a piston cylinder, if it's free to move, what that means is the pressure is going to be constant, right? Because the pressure, that's why it's moving, right? It's moving, you can think of it is that it's moving in order to change the volume so as to keep the pressure constant, right? So we find the pressure, but once we know the pressure, that pressure is not going to change. This is, of course, different if there's stops that block the piston at some point, right? But that's not the case. So in this case, the pressure is constant. So let's find what that pressure is going to be. So we know that the pressure has to exactly balance the weight of the piston, right? Plus the pressure, the atmospheric pressure from the other side. So the pressure inside, that's bad handwriting. Okay, the pressure inside, first we have to balance the atmospheric pressure. We know that already. But then we have to support, in addition to that, the weight of the piston cylinder. Well, the pressure by the weight of the piston cylinder. Now, pressure is force over area. The force we're talking about is the weight, and the area is the area of the piston. So if we do mg, where m is the mass of the cylinder, m is the mass of the piston, that's the weight of the piston divided by the area. It's circular, so it's pi over 4. Diameter is 22 centimeters squared. This, if we plug in all the right values, so 97,500 pascals plus 10 kilograms times 9.8 pi over 4 and 0.22 squared. If you do all this, you should get 100.8 kilopascals. That's the pressure inside the cylinder, and that won't change. So we have 100.8 kilopascals, which we can still round to 0.1 megapascals just to keep things easy for us. Now, that means initially our state 1 is at 0.1 megapascals, and oh yes, they give us the temperature is minus 10 degrees Celsius. But they want to know the volume change, so we need to find the initial volume, obviously. They want to know the enthalpy change, so we need to find the enthalpy as well. So let's start looking at some tables. So here we are at the refrigerant R134A tables. Now, our pressure we're looking for is 0.1. So it's obviously going to be in this box somewhere. And we know we're at a temperature of minus 10. So all the values we want are going to be found here. So specific volume-wise, this is our specific volume here. And enthalpy-wise, this is our enthalpy. So we don't want the specific volume, though. We want the volume. So we have to take specific volume and multiply it by the mass of material in the piston, right? And we're told there's 0.9 kilograms of refrigerant. So 0.9 kilograms times 0.20686 gives us a volume, an initial volume of 0.186. So let's just write that down. 0.186 meters cubed. This is our initial volume. And the enthalpy, well, the enthalpy, we just read it off. 244.7 kilojoules per kilogram. Was it 17 or 07? No, 244.7, sorry. 244.7 kilojoules per kilogram. Okay, that's a good start. Now, we already spoke about the pressure and how the pressure is not going to change. So P2 is 0.1 megapascals as well. And in the question, they tell us the temperature is heated, it's heated to 20. So let's go see what's going on there. So we're already a superheated vapor here, so we know we're definitely still a superheated vapor now. So still in the same box. So let's just undo our markings for now, though. Now we're looking at the 20 line. We're looking at this guy. So we got the enthalpy here, we got the specific volume here. So as before, we're going to multiply our mass of 0.9 kilograms of refrigerant times 0.23349 meters cubed per kilogram. And that gives us a volume of 0.21. So let's record that here. .21 meters cubed. And our enthalpy is 270.02. Come on. There we go. 270.02 kilojoules per kilogram. So the difference in volume is going to be V2 minus V1. So 0.21 minus 0.186. So minus 0.186. And that gives us a change in volume of 0.024 meters cubed. And our change in enthalpy is H2 minus H1, which is 270.02 kilojoules per kilogram minus 244.7 kilojoules per kilogram. So 270.7 gives us a change in enthalpy of 25.32 kilojoules per kilogram, right? Now this is enthalpy per unit mass. If we want to do actual enthalpy, like absolute amount of enthalpy we have, we just multiply this by the mass of the fluid, which is 0.9 for us. And I think that answers everything they ask here. Pressure, volume change, enthalpy change. Yeah, we got it. All right, thank you very much.